So the last thing we discussed last class was this property. Okay, we have proven that the exponential of the log is the argument. Okay, so exponential of exponential of the log of z is z. Okay, the value of the exponential. But the log of the exponential is not z, it's z plus or minus 2n pi I. Okay, so you gotta be careful there. And moreover, we are going to solve an example. So let z be equal to exponential of pi I. Exponential of pi I. So we need to compute the logarithm of z. This is the logarithm of the absolute value of this z. Okay, the modulus plus I times the argument of pi I. Exponential of pi I. Now this one's simple. Okay, the exponential of pi I, remember this is a pure imaginary number, pi. Okay, so the exponential of I pi has modulus equal to 1. The log of 1 is 0, so you get 0 here plus I times the argument of exponential of I pi. Now this is I times the argument of I pi. You tell me, what's the argument of I pi? Well, let's locate this number in our diagram, right? So pi means, well, exponential of I pi is the same as cos of pi plus or minus plus sine I sine of pi. So this number is located on the unit circle. The question is, where is it? Which what part of the unit circle, right? Well, the angle here, theta, is pi. So this number is located down there. Okay? This is the number ei pi. Thus, what's the argument? Well, the argument is clearly pi, but not also pi, because this argument right here, the one we're utilizing, is multi-valued. This is not the principal value of the argument. So you need to add or subtract integer multiples of 2 pi I. So n equal to 0, 1, 2, blah, blah, blah. Okay? So the log of this number is I pi plus or minus. Thus, the log of exponential of pi I is I pi plus or minus 2 n I pi. Okay? However, the principal value of the logarithm of ei pi, what is it? Obviously, it's going to be 0, okay, because the argument of the modulus of exponential of I pi is 1. So log of 1 is equal to 0 plus I times, now the capital argument of the same number, exponential of I pi. What's the principal value of that argument? What is the principal value of that argument? Well, the argument of I pi, principal value of the argument, is a function, so this function, right? This number belongs in negative pi, so you don't touch negative pi, and pi is included. Well, ei pi, the argument is exactly equal to pi. So you get here I pi. Alright? So you have two things there. The normal logarithm, the complex logarithm of this number is, this argument or the principal value of the argument plus or minus rotations. And the principal value of the argument, the principal value of the logarithm is just this sort of a principal value of the argument times I. And the principal value of the argument, of course, is pi. It's down there, in that interval. Okay. Now let me check something out here. Let me check. somehow extends the, but this function, this notion of logarithm extends the usual real notion of, well, the usual notion of real logarithm. That's what I want to say. The usual notion of real logarithm. Why, guys? Why does this function, right, the complex logarithm, extend the usual real logarithm? Okay, indeed, if x is real, sorry, z is real, so that means that z is equal to x, right? So it's real part. Let me just take this out of my way. It's really annoying. Okay, x equal to z, so z is equal to its real part. X equal to its real part, right? What are you gonna get there? Then the logarithm of z is equal to the logarithm of the absolute value of z plus I times the argument of this this logarithm. Now, not only that, let me utilize, okay, the principal value of the logarithm. So if you do that, you need to adjust here for a capital L and here for a capital A. Okay? Now we're fine, because this is a single valued function, so it's much more convenient. Okay? Guys, let me ask you guys. Let me ask you what happened here. Oops. Let me ask you one thing. What's the logarithm of absolute value of z? Well, z is equal to x, right? Not only real, but we need to ask for x to be positive, strictly positive, because this logarithm does not exist for 0, so x cannot be 0. Okay, and for real numbers either. For negative numbers, okay? So if x is positive, so z equal x positive, we have here the usual logarithm of x, okay? Plus I times the argument of x, z is equal to x. Now if you look at the real line right here, okay, so x and y, your x is right here. Question is, what's the argument? What is the argument of a real number? Positive real number, not negative but positive. What is the argument? Think about that quickly. And what's the argument of x? Well, the principal value of the argument is something lying between negative pi and pi in there. Okay, so it must be 0. Okay, for a real positive, this argument is just 0. So you're going to get here logarithm of z, principal value of the logarithm equal ln of x plus 0. Okay, so that's why the complex logarithm does extend the real one. Okay, this notion of real logarithm. Okay, so in reality, oops, this thing is turning off. In reality, the notion of complex logarithm is a generalization of the notion of real logarithm. Okay, so now, guys, I'd like to, remind you of something here. Remember, okay, this is the important point. If x is positive, for x positive, then the logarithm of z is equal to the logarithm, the usual logarithm of x, okay? Now, if somehow, right, x negative did have a logarithm, complex logarithm, okay, then that would be a real extension of the I mean, that would be an example about the fact that log z is a real extension, is a cool extension of the usual real logarithm of x, because the logarithm of x for x negative does not exist. So if eventually, if we could evaluate here, we could evaluate at a point which is negative, real negative, then we would have an example of an extension. So now, if x is negative, so real negative, then capital L n of, let's say, z equal x, okay? So this is the principal value of the logarithm of z is the logarithm of absolute value z plus I times capital argument of z, okay? By definition, what is the logarithm absolute value of z? Now we are in a different situation here. Now x is negative, so x belongs in the negative axis of coordinate, right? And it's real. So what's the logarithm of the absolute value of z? Well, it's going to be the absolute value of x. So this is the logarithm of the absolute value of x. X is negative. The absolute value of x must be positive. Okay? So you got this sort of equality. The important thing here is the argument. What is the argument of x? Think about it. What is the argument in this precise case, right? Precise example of z equal to x, x being negative. What is the principal value of the argument of x? Well, it's not negative pi, because the argument, this thing right here, the principal value of the argument belongs in negative pi pi, but it's open at negative pi. So it cannot be negative pi. You can't do this. Go from here to there. Okay? So what is it? It's gonna be pi. Okay, so negative numbers, the principal value of negative numbers, the principal value of the argument of negative numbers is always pi. So I need to plug in pi there. Say, you can't do this from here to there. No, you gotta go from here to there, counting the theta positively in the positive direction up until you get pi to the point pi. All right. The argument of a complex number, a real number which is negative, the principal value of the argument is not negative pi, because negative pi is not in that interval. Okay? So you get this. You get the logarithm of z is the logarithm of negative x plus I pi. If x is negative. Why did I write negative x here? Because if x is negative, negative x is positive. The logarithm of a negative number does not exist. Okay? So actually there we can see clearly, guys, that the complex logarithm is an extension of the usual real logarithm. Okay? So we have a formula for the logarithm now of negative numbers. And that we didn't have in the case of the real logarithm. Now, the logarithm, the principal value of the logarithm, the logarithm, the complex logarithm is an analytic function in the whole of C minus the negative axis of coordinates. Okay? So what's the domain of analyticity of the complex logarithm? And why is it analytic there? Why is it analytic in C except for the negative axis of coordinates? So I'm saying that if this is the complex, if this is C, right? You take this side of the axis of coordinates, the real axis of coordinates, which is the negative part, and this is the domain of analyticity. So here the logarithm of z is analytic. Analytic. Why? Why is the domain of analyticity of z the whole of c minus that axis there? Well, the reason is that when you turn, see, when you make a full turn of 2 pi radians, right? So for example, you're standing right here at this point. Then you move from this point continuously, all right? Continuously. Well, what's going to happen at the negative axis of coordinates? The argument will jump into 2 pi n. Remember when we had this plotting, when we computed the logarithm, and we said the logarithm is not a single valued function but a multi-valued function. What happened with the values of the logarithm? Well, what happens here is that they indeed they jump. So what I mean, this distance is 2 pi I indeed. Okay, so it's along the imaginary axis of coordinate. So all of them, so two consecutive measures of the logarithm are always separated by 2 pi I. So when I make a full rotation, okay, of 2 pi radians, right, I'm gonna find two different values of the complex logarithm whenever I cross the real negative axis of coordinates. You lose continuity here at that point. So that branch is called the I mean, this is a branch cut. We're not going to step there in this course, right? Because that's that topic belongs to a different course, right? Which is multi-valued functions and Riemann surfaces, and we're not going to stay there. Okay. The only thing you need to retain is that the logarithm is analytic right here, everywhere. Okay. So that's the domain of analyticity. The domain of analyticity of the logarithm of z is c minus the negative real axis. Okay? So it's analytic there. It's analytic everywhere there on, say, c, minus along the real axis of coordinates. Okay? So this is something you need to bear in mind, guys. Okay? I don't know what's going on with the connection today. So, sorry, guys. Give me a quick second, because the internet is on and off. Okay, guys. All right. So we have this situation where we have a multi-valued function. We know the domain of analyticity of this function, and it extends, right? This function extends in its domain the real function, the real logarithm. So in the real world, we know that the logarithm of x derivative is 1 over x. The same thing happened here, and the answer is yes. Okay? So in its domain of analyticity, so there, analyticity, the logarithm, the complex logarithm, satisfies. So in its domain of analyticity, the complex logarithm satisfies logarithm of z derivative equal 1 over z. For z not 0. Okay. So remember, we can't evaluate. Well, question: can we evaluate the logarithm at 0, the functional logarithm at 0? The answer is no, we can't. Not even the principal value of the logarithm. When you try to plug in 0 here, you already have problems there. The log of 0 doesn't exist. It's negative infinity. And the argument 0 does not exist either. It's not well defined because as you approach 0, the argument vanishes, right? There's no clear notion of what's the argument of 0, the point 0. Okay? But certainly we can proceed as in the real world, right? And then we can define, from this notion and from this property, we can define powers. Okay? So that's one property you need to keep in the pocket. And by the way, I need to tell you the chain rule is valid here as well. So the chain rule, when we multiply and compose functions, right? The chain rule is valid as well. The chain rule is valid as well for the concept of differentiation. This is something I should have told you the other day, but in reality we proved that. I mean, we didn't prove. We mentioned that the chain that the derivative of the product is, you know, the usual thing, the quotients, the addition, but I didn't tell you about the chain rule, and it is valid indeed in this case. So so the chain rule is as follows. Chain rule says that if you take the derivative f of g, the derivative of this function at the point z, then you're going to get f prime at g of z times g prime of z. Okay? So first, you to compute the derivative of the composition, or the composite function, or composite function, you take the derivative of the first one, you evaluate at the second one g of z, and then you take the derivative of the second one. So example, compute the derivative of the logarithm of z squared plus 3z plus 2. Derivative. Okay? So now this is the logarithm we studied today. This is a polynomial. Alright, we're going to get into polynomials in a few classes, but I mentioned that polynomials are entire, everywhere, analytic. Okay? So this is a complex polynomial. And I told you what's a rule to differentiate complex polynomial, right? Polynomials. So this is the rule for differentiation of monomials. What was it? Remember, it was derivative of z power n equal n z power n minus 1. Okay, for monomials, here we have an addition of monomials. So what can we do here? Well, something super straightforward. We can apply the chain rule there, and this complex rule down here, the derivative of the logarithm. What are you gonna get there? We get that the derivative of the log of z squared plus 3z plus 2, derivative is 1 over this argument because of the chain rule. Okay? So this is 1 over z squared plus 3z plus 2 times the derivative of g. Okay? So here, before we do that. So before we do that, I'm gonna show you how to do this using the chain rule. So first of all, let f of z be equal to the outermost function, which is the logarithm of z. And g of z be the polynomial. So z squared plus 3z plus 2. Okay? So what do we get there? What's f of prime of z? F of prime of z is 1 over z, because f is the logarithm. So this is what I told you. What's g prime of z? Well, according to the rule of differentiation for our monomials, this is 2z plus 3. So now FO composite g, z at the point z, what is it? FOG at the point z. Well, this is f at g of z. What is it f at g of z? It's going to be the logarithm evaluated at g of z. G g of z is z squared plus 3z plus 2. This is the function we would like to compute the derivative on, right? So we want the derivative of this composite function. So f of g derivative, okay, the derivative of the composite, according to the rule, will be f prime at g of z. Well, f prime is down there, up there. F prime evaluated at g of z. So it's going to be 1 over z squared plus 3z plus 2. Okay? Times g prime of z. G prime of z is 2z plus 3. So again, I'm not going to go back to, and that's it. I'm not going to go back to calc 1, right? But this is what you do actually. You don't need to do that, right? It's just an explanation of the chain rule. But this is what you do, and this is what we did back in calc 1 or calc 2. So give me a second, I have connection problems here. Someone is from IT sent me an email, right? Someone sent me an email because the internet is not working, and I'm uploading your classes today. Okay, so what I'm saying is you don't need to formulate, all right, the whole thing in terms of composite functions and stuff. No, if you know how to do that, if you know how to do that, you just do it. That's what I would have done here. The logarithm of z squared plus 3z plus 2 derivative. Well, I do 1 over the argument times the derivative of the argument, which is 2z plus 3. That's it. Okay. So again, the same stuff we did in calc 2. You can do that right away. You no need to formulate the whole thing in terms of composite. Now, general powers here. Okay, so that's something that comes out of this rule, the differentiation rule, plus let me clean up here as well, plus the definition of the logarithm, and a trick, small trick that we're gonna tackle right now. Okay, so this is as follows. This is as follows, guys. Look. Let C be a complex number and Z be a complex number as well. Then we define. So now the good thing is that everything is complex here. So in the complex world, we have more like tools, and like they're different tools, and they're much more flexible than like not flexible, the opposite, rigid than the tools we have in the real world. So what does that mean? Well, it means that when you're doing something, the conclusions are pretty much automatic. Okay, because there's only one way to do things, pretty much. So you're gonna feel that in the idea in a few weeks ahead. All right. So I need z not to be 0. So we define z power c to be. So what are we gonna do here? We're gonna utilize our trick. I'm going to use the fact that the exponential of the logarithm is z. The exponential of the logarithm of z is z. So I'm going to write here the exponential of the logarithm of this same number, z power c. Okay? So from the definition of logarithm of z, it is easy to see that the logarithm of a power b is b times the log true? Well, because the logarithm, the complex logarithm for a and 0 and b complex, okay? Why is that true? Well, it's because this rule is true for the real logarithm, okay? So since the definition of the complex logarithm includes a real logarithm, you apply the property there, okay? So we have this property as well. Thus we get this, z power c equal exponential of the logarithm. Then I'm going to take the c out of there, back down there. So c times the logarithm of z. Okay? So this is the definition of a power. Okay? So this is our definition of a general complex power. Complex power. Okay, so this definition wasn't available in the real world, by the way. Okay, the sort of complex power, right? It didn't make any sense here. All right, but now it does through this formula. Now this formula includes the log of z. That's why this is well defined. This function right here, z power c, is indeed a complex function. All right, and it's given by the logarithm there. So this formula, it's something we would like to keep in the pocket. Now this is a usual power. It's a general complex power. If we utilize the complex logarithm, but the principal value of the logarithm there, we get the principal value. Is it called the principal value? Let me check. Yeah. Principal value of the power, the complex power. So z power c, you have the right here to utilize the complex principal value of the logarithm of z. Okay? And this is valid for z non-zero. Remember, z non-zero because I cannot evaluate the logarithm at any zero number. Okay? So that wouldn't be allowed. They're trying to fix the connection. I think there's a little problem with the BB connection, so I need to upload all of these videos later on to BBE, and then I'm having problem there. Not the videos, but the links, and I'm having a little bit of a problem there because it doesn't want to connect. Okay, so we have that definition, right? And what can we do with this stuff? Well, important stuff we can do, and it's super nice what we can do actually with the definition of this power, complex power. We can, for example, compute things that we were not able to compute before. So example, and let me see my slide. Yeah. So example I power. So compute I power I. Now this is amazing. I power I, because I is the square root of -1. Okay, so I'm asking you to compute the square root of -1 power the root of -1. The complex root. I mean the square root of -1. So that's something you cannot do in the real world, but we can by utilizing this formula right here. Okay. So I power 1, the solution here, I power I is, so both z and c are I. So I'm going to replace there c by I, and then z by I as well. All right? Now let's check out, what's the logarithm of I? Well, this is the logarithm of the absolute value of I plus I times the argument of I. All right? So again, what's that? Well, the logarithm of the absolute value of I, the absolute value of I is 1, right? Because I is located up there. Okay, so the modulus of I is 1. The distance to 0 is 1. So 1, 0, you get 0, plus I times, what's the argument of I? It's 90 degrees, so pi over 2 plus or minus 2 and I pi. And from 0 to infinity. Alright? So this is the logarithm of I. So let's plug it in there, into the exponential. Let's plug it into the exponential. What are you going to get there, guys? Sorry. If you plug it in the exponential by definition, so we get I power I equal exponential, this exponential I times the log of I, which is computed down there. So I pi over 2 plus or minus 2 and I pi with n equals 0 to infinity. Okay, so a natural number. Good, but I squared is negative 1, so I times I is negative 1, I times I is negative 1. Thus, you're going to get here the exponential of negative pi over 2 plus or minus 2 and pi. Okay, and that's, honestly, that's well, negative and plus. That's extremely weird. That's extremely weird because I is a super, it's by definition the complex unit. I complex unit. So the complex unit power, the complex unit is a real number. Purely real. It's pure real number. Okay? So you can locate those numbers along the real line indeed. However, I power I, if you utilize the principal value, however, the principal value of I power I is, so the principal value of I power I is, and here you take EI, principal value of the logarithm of I. What do you get there? Exponential of I. The logarithm of I, principal value of the logarithm of I, will be the logarithm absolute value of I, which is 0, plus I times principal value of the argument of I. What is the principal value of the argument of I? Well, the argument of I is pi over 2 plus minus any rotation, okay? So it's going to be 90 degrees pi over 2 because that's already a principal value. That's a principal argument. So you get here, you get to plug pi over 2 right away times I. Okay, so I times, oops, made a mess here. I times I pi over 2. So you're neglecting this part, okay, in the computation of the principal value of the power. So thus you get the exponential of negative pi over 2 right away. Negative pi over 2. Okay? This is the principal value of the power, I power I. And yet one more example. Let me check my time, guys, here. 30 minutes. Okay, we have 12 minutes. Still 12 minutes to go. So, yet another example, guys, is given by the following thing. Yet another example. This thing is going to collapse now. I don't think this is another. So I'm going to use a bunch of serviettes, a bunch of tissues, okay? All right. So yet another example. Compute the number 1 plus I power 2 minus I. 1 plus I power 2 minus I. Okay, so let's see what we get there. So by definition, this is, so solution, this is what? 1 plus I power 2 minus I, by definition, is the exponential of 2 minus I times the logarithm of 1 plus I. Okay? It's like this is your C and this is your Z. Alright? So now what do you get there? you get to compute this logarithm of 1 plus I. We have done that before, right? So the logarithm of 1 plus I was the logarithm, absolute value of 1 plus I, plus I times the argument of 1 plus I. What is this? This is the logarithm of square root of 2, remember? Plus I times the argument of I, 1 plus I was pi over 4 plus or minus the rotation. We get here pi over 4, which is the principal value of the argument, plus or minus the rotations in 2 pi radians. Okay, so we plug that back in there, and we get that 1 plus I power 2 minus I is the exponential of 2 minus I times this product right here. ln square root of 2 plus I times, and we need to use a square bracket there, pi over 4 plus or minus 2 and pi. Okay, so we get this stuff right in there. And now we sort of we distribute and multiply. Okay, so you get there the exponential of 2 times ln square root of 2 plus 2 times I pi over 4 plus 2 and pi. So you can write that way, pi over 2, because 2 divided by 4, right, is 1/2. So pi over 2 plus or minus, then 2 times 2 is 4, and pi. All right? And then you get to multiply the whole thing by negative I. So negative I, ln square root of 2, and then negative I times I, that's positive 1, plus pi over 4, plus or minus 2 and pi. Now we have here real part and an imaginary part. Okay, so we collect like terms. Okay, ln of square root of 2, we've seen this before, is 1/2 of ln of 2. 1/2 divided by 2, you get the ln of 2. So this is ln of exponential of ln of 2. Real part. So the real part is plus pi over 4 plus or minus 2 and pi there, and then the imaginary part plus the imaginary part, which is pi over 2 here, plus or minus 4 and pi, minus the ln square root of 2. That's your imaginary part. Now this is exponentiated, all right? So what we can do actually is to utilize Euler's formula there. So I'm gonna, this is like real part and imaginary part, and there's one exponential there. So remember that the exponential, so recall that the exponential of a plus ib, or a alpha plus I beta, for alpha and beta real, right? This exponential is the exponential of alpha times the exponential of I beta. This is the exponential of alpha times cos of beta plus I sine beta. Okay? By Euler's formula here. That's what we're going to do. So, what do you get there? We get that 1 plus I power 2 minus I is the exponential of ln of square root of 2 plus pi over 4 plus minus 2 and pi, and then you utilize the polar part here. It's going to be the cosine of this angle right there, cosine of the imaginary part. So pi over 2, pi over 2, plus or minus 4 and pi. Plus or minus 4 and pi, minus ln of 2, square root of 2, okay? And then plus I sine of the same stuff, pi over 2, plus or minus 4 and pi, minus ln of the square root of 2. Okay, guys? And then I think that's it. Right? I think that's exactly it. Yeah. I think that's exactly it. Can we do something? Look at this. Okay, there's something we can do right here, and it's good for your trigonometrical knowledge. Okay, your knowledge on trigonometrical functions. So, which you are going to utilize a lot in this course. Okay, so what is going on here in this precise example? Let me check my time. Yeah, 5 minutes. The cos and the sine are 2 pi periodic functions. They are trigonometric periodic functions. The period is 2 pi. So the cos of this stuff is the cos of pi over 2 plus or minus 4 in pi. See? 4 in pi. Cos of alpha plus 4 or minus 4 in pi. You don't do nothing because 4 in pi is a multiple of the period of this function, which is 2 pi. So the cos of this stuff is the same as the cos of pi over 2 minus ln of the square root of 2. Same thing here. The sine is 2 pi periodic, so the argument of this stuff can be shrunk into the argument pi over 2 minus ln of 2. Okay? So you're left here. So this stuff right there is the same as the cos of pi over 2 minus ln of square root of 2. And this one, this whole thing is the sine of pi over 2 minus ln of the square root of 2. Now, the cos of pi over 2 minus alpha, what is it, the cos? Well, the cos of this expression is the cos of pi over 2, cos of ln of 2. There's a minus of plus sine times sine, okay? And likewise here, the sine of pi 2 minus ln is the sine pi 2 cos of this one, minus 0. Okay, because the cos of pi over 2 is 0. So you're going to get here, as the final remark, that 1 plus I power 2 minus I will be equal to. And there's one important thing to be noticed there. The exponential of the ln of square root of 2 is nothing else but square root of 2 there. Okay? So you can work out this part as well. You can work out this part as well. Guys, I think it was 2 here. Sorry, it wasn't the square root of 2. It was 2. So you're gonna get here exponential of ln of 2. That's 2. Then the exponential of pi over 4 plus or minus 2 and pi. Okay, and then inside the bracket you get, like I said before, the cos of pi over 2 is 0. So you get sine of pi over 2, which is 1 sine of L n of square root of 2. Then plus I, this I right here. And then you get the sine of pi over 2 in cosine of ln square root of 2. Cosine of ln square root of 2. So you get this expression right in there. Okay? It's a little bit long, the procedure and all that stuff, but actually it's really straightforward. Okay? Okay, guys. Really straightforward indeed. Really straightforward indeed. Alright? Right. So you check it out, okay? You compare with my result. And it was just an example, okay? So this is the sort of things you're going to do in a quiz, indeed. You're going to get to do this, indeed, okay? Right. Right. Now, this is z power c. What happens if we take, for example, now the definition? Now a power z. Okay, for a non-zero. So let us define. For, I think a is non-zero. What's the requirement here? No, any. For any complex number a. Now we need a power z. Okay. not z power a or z power c. Now it's c power z. A power z. So what is it? Same thing. By definition, this is the exponential of the logarithm of a power z. But z can come out of the logarithm. So this is going to be the exponential of z times the logarithm of a. Okay? So we define a power z to be z times the logarithm of a. Okay? It's just another definition that will allow us to do mathematics, computation. All right, guys? So now I'm gonna give you a set of exercises for you to practice and all that stuff, okay? But you gotta follow the sections that I told you about in the email, okay? So sections 13.1, 2, 3, and 4, you're ready to work on your own, okay? So see you next time, guys, and keep studying and watch the videos, okay? Thank you so much. Bye.